Okay, so welcome to the second talk of the day. Today we are very happy to have Prof. Subhendra Mohanty from IIT Kanpur. He was faculty member here for many number of years. He has worked on various topics in particle physics, astrophysics, cosmology, astroparticle physics, and whatnot.
String theory.
Yeah, string theory. No, string theory. Yeah, okay, string theory. No? Yeah, and this is something I think is doing it for the first time. Right? Effective theories at finite temperature.
Yeah.
This was done 2 months ago. Okay, thank you.
Thanks, guys, for listening to my talk on this busy day. And so this is going to be a theoretical sort of subject that I'm going to calculate effective theories, effective theories, and I'm going to motivate that why it's important to, or sometimes necessary to calculate this effective theories with Wilson coefficients at finite temperature. So let me start by why we need to do this. This talk is based on this paper I wrote with Jyoti. You can look up the details of this maths which I go through rapidly. If you are interested, you can look it up in this. So let's start with the effective theory, and I'll tell you that if you take this theory and try to calculate something in finite temperature, for instance, phase transition. Now, phase transitions are coming back in importance because during phase transitions, if they are of first order, then they have gravitational waves, you have produce gravitational waves, which you can observe as stochastic gravitational waves in various sources. So that is a prime motivation for calculating these phase transitions again and seeing if something is first order or not. Earlier, phase transitions were calculated for baryogenesis. So this was a big game in 1990s and so on. Now the motivation is different. It's to see if you can predict gravitational waves. Okay. And the other thing in particle physics is we don't know which is the correct UV theory. So you find effective theory that you integrate out the heavy particles and then write the effective theory for the light particles and test that in colliders, cosmology, and various things. And what that does is that gives you this high dimensional operators, dimension 6, dimension 8, and so on. And if you find evidence for this, you can from any experiment, then you can go back and see what is the UV theory which gives you this. So for instance, if I take the Higgs and I write a dimension 6 operator, I could write dimension 8 and so on. And in this, not all these A2, A4, these are what I'm calling Wilson coefficients, these are not all independent. If I impose this condition, that there is a minima at h equal to v, v is the 246 GeV, and the second derivative at the minima is your observed Higgs mass, 125 GeV. So with these two conditions, then I have only two independent, so this is the only free parameter left. So what that tells you is that your quadratic term is of this kind, which has a A6 in it, and your quartic coupling is of this kind, and you have a after imposing these two conditions. So what that means is that if you had an effective theory, if there was a A6 and you did a Higgs scattering at colliders, then your coupling would be this. So this part is known, and you will measure A6 from there. So there is a usefulness of having this effective theories where you can measure these couplings in various experiments. Okay. So the application I have in mind is that you take that potential, put it at finite temperature. So what happens is that this is the shape of the potential now, okay. And at higher temperature, early universe would have been like this, okay. And it goes down here and then it goes down here. So when a situation happens when we have two minima which are degenerate, then the universe, the phi field everywhere was at 0, the minima at this high temperature, okay. And at low temperature it becomes this. There will be a tunneling, okay, or this. There will be a tunneling from this vacuum to this vacuum, and there is a delta V potential difference which will be released as thermal energy. So that's called the latent heat, and that will go to producing gravitational waves. So this is called the first order phase transition, and that's the shape of the change in potential with temperature that you are looking for. The other could be what's called a crossover or a second order, where the shape of the potential is such that it just rolls down from here to here without a sudden release in energy. Okay. So this doesn't give you gravitational waves, but this could also happen. So now we are looking for ways in which to models which will predict your first order phase transition, and because that will have your observational consequences. So this was seen since a while that if you add to so in the standard model, the phase transition is second order. So the first order phase transition doesn't happen for the Higgs. But it was seen that if you add a singlet, for instance, to your standard model, then the singlet rule, which is known, I'll explain it later, that what you need is an extra gauge boson, so a scalar or a vector gauge boson in the loop which couples to the Higgs to give you that potential, the shape of the potential, which will give you a first order phase transition. So the simplest case of extra scalar is extra gauge boson is a singlet scalar pi. So if you have this coupling, then this is the region with the lambda and the mass which will give you a first order phase transition. Okay, if you do the whole UV theory.
So there is one table by
Grosjean. Yeah, the same thing. So they are doing the same thing.
Right. In SMEFT they showed that you can have. In SMEFT they showed that.
Yes. So that was the issue that in EFT the parameter space is different from what you get in the full theory. So this was pointed out by so he is preempting the thing that so this was in the UV theory. Then it was seen by Grosjean, Savan, all that.
First one was that also had Vinitra. First one also had Vinitra.
Okay, yeah. So those guys were the first to point out that if we have a scalar at not too high mass, it will give you a phase transition, and then they did it in the effective theory. So what these guys did was that they looked at these effective theories, for instance the singlet effective theories. So what they found out was that the parameter space which you get from starting with this theory and calculating the phase transition, and starting with the UV theory and calculating the phase transition, they are different. Okay. Also, this one breaks down the place where the phase transition takes place. The ACX becomes equal to A8 and so on. So the perturbation breaks down. So basically, the idea was what they pointed out was doing this at finite temperature somehow doesn't work, okay, and it's not difficult to see why that should be so. Because you see the particle that we are talking about, this was not too heavy, like same range as the electroweak. And if you are talking about changing the potential at about 500 GeV, then at that temperature, the particle which you integrated out, the singlet, will be there in the heat bath. Whereas if you start with this theory and did a finite temperature calculation, your heat bath particles will only be your H and the standard model particles. So there is so when you integrate out to get a low energy theory, you forget that at finite temperature those particles are again accessible. So the solution to this problem is that when you integrate out a heavy scale to calculate this A6 higher dimensional operator, you have to take into account that do it at finite temperature so that these coefficients automatically change at high temperature to do it, put account the heat bath and those heavy particles. Okay. So that was the thing, we need to calculate the finite temperature corrections to this Wilson coefficients. And this I will do. So this heat kernel method of calculating effective theories is something that my collaborator Joydeep has been doing for many years. Okay, so he has perfected this. So I'll explain this basic heat kernel method. So this is the thing I will do slowly. After that, the algebra I'll skip, but this part is something general which is of usefulness even apart from this problem that I am talking about. And then what we did was took this method and applied it at finite temperature to get the effective theories. Okay. So we start with the second order elliptic operator. So that means that here the time and the space derivatives dt square and dx square should have the same sign, which means you have to go to the Euclidean space. With the opposite sign, it's called a hyperbolic operator. And this is the potential, okay, and this is the mass square. So your Lagrangian is this operator with quadratic into these two fields, which means that u, suppose you take lambda 5 to the 4th theory, that means there u would be lambda 5 square. Okay, you take out 2. Then what you do is you take this field and take the fluctuations around the classical, okay, and Taylor expand the Lagrangian and write the Lagrangian as a quadratic. So the first order term delta L upon delta phi would be 0 at the classical. Okay. The second derivative would give you this u, and you will get a bilinear term like that in the fluctuations. Okay. So the effective theory action, the one loop effective action is that you integrated out the fluctuations for this operator, okay, and give a classical Lagrangian. Okay. Now remember this d mu would involve background gauge field. So background gauge field, okay. So it could be non-abelian. This could also involve gravity. So you have a crystal connection here. So that will, you can do the same thing for gravity. And
So one question. So can there be I mu? So this I is not here as I can see. So for this case.
yeah. So we have gone to now a Euclidean time to make it. Yeah, thank you. So we want the space and the time to be of the same at the same footing. Otherwise, this interval becomes indeterminate. I'll show you in a solution. You want this to be negative. This. So we have gone to Euclidean time where I is absorbed as a t. Yeah, thank you.
So you only classical part or the second derivative W.
Uh-huh.
Is that the classical?
No, this is the one loop. So okay, so there will be a classical still e to the I classical. So the total action will be a classical plus the W. Okay, and I am writing the W part.
You are taking the determinant.
Yeah, I take the determinant there. Yeah, so basically there will be,
Up to second derivative.
yeah, up to second derivative that will, because I only know how to calculate bilinear, the path integral of bilinear terms. So as you predicted, we take the determinant. So this path integral is the determinant of this operator formally, and we are taking complex fields, so that is determinant minus 1. If it was real, then this would be minus half. Okay. And so that is just following the Gaussian formula. Okay. Now take the log of both sides. So this is log determinant of delta, okay, which is also trace of log. Okay. And by trace we mean that if it's in the position space, then you have in between position operators and integrated over all space, and traced over if it has spinor indices, you trace over the spinor indices, you also trace over the internal indices for the gauge part. So you trace over all degrees of freedom to get finally a scalar. Okay. So next you write an identity like this. Okay. So to check how this works, just take derivative with delta on both sides and see that you'll get both sides will give you the same result. So starting with this identity, okay, for the operator, take the trace. So the trace of this log will be W. So the trace on this side will be trace of this operator. So by trace again I mean sandwich is in position eigenstates and integrated over all volume. Okay. So there is a different way of writing this operator. So this is the thing we are trying to calculate, the effective operator after integrating out a heavy part.
U is
Huh?
U is what?
So U is the coupling. So for instance, if you have lambda 5 to the 4th here, then you take out 2 phi's. So it's delta. So it is lambda 5 to the 5 square.
Okay. The potential part.
Potential part.
Isn't U at 5 classical?
U at 5 classical. That's it. So ultimately we are calculating effective theory in the classical background. Okay. So now I go to something else and then I'll connect that W with this thing. So I define something called a heat kernel, which is you take this operator and sandwich between x and y. These are position eigenstates. These are different. So this will depend, and there is this parameter s. Okay. So this obeys this heat equation clearly. Okay. So this is called heat equation because this is similar to what you see for the diffusion or heat equations, and some generalization of that. And you put initial conditions that when s is equal to 0, x and y inner product is just delta x. So this one is my initial condition, and this is the equation. Okay. So if I solve this, I can get this quantity e to the delta s. Okay. So how? So remember the last transparency I said w is trace of e to the s. Trace means xx of this. So this is the same thing as this kxx at the coincidence limit, that means x is equal to y. I calculate this, I solve this equation of k, okay, for this general operator. Then I take it at the coincidence limit and I do this integral over s. If I am able to do that, then I will get this w, which is my one loop effective action.
This is a typo, so even after writing k, since you have written this trace.
Trace is still, so kxx integrated over all volume. So you should remember this is the action. So action is d4x. So that is the d4x which you want for that. So the x, this is inner product. And then you integrate over that. Okay, so suppose there are no interactions, then this is my operator, and in this operator this has the solution. Easy to check. And what I am looking for is the coincidence limit always. So the coincidence limit will give me this factor, whereas d minus 2. This part will go away, and e to the power s n square. So this will stay. Now,
So D is the dimension.
what?
D is what number of dimensions.
D is the number dimension. Yes. So here, as I said, that this this does not work if this has indeterminate. If it was a Lorentzian signature. The convergence doesn't work, which is why you have to go to the Euclidean metric and do this calculation for the convergence. Otherwise, these factors do not have a definite sign and there is no convergence. Okay. So now what I'll do is I'll switch from s to t because now there is no confusion that this is not time. This s is some auxiliary variable, that was not time. But to conform to the notation of our paper, because I start putting in formulas from our paper, I'll switch from s to t. So this is the total solution for the heat kernel. I'll take it as the solution for the free part times some extra factor, and we'll say that these factors are power series in t. Okay, so this is the power law of k, and it will depend upon two things, x and y, summed over k. So, and these guys are called Heat kernel coefficients.
So when we are saying free theory,
Free theory means there is no u.
and in terms of
This is u.
so in terms of temperature,
No, temperature is not yet there. So what first I'm going to do is integrate out these things at zero temperature. So there is a zero temperature effective action first. Okay, using this, and then I'll generalize to finite temperature.
this is all still zero temperature.
There is zero. So I'm going to show how the zero temperature effective action comes out using this heat kernel. Okay, so this is an answer, and what we'll see later is this power series in K will turn out to be power series in 1 by m square in effective action. So this basically gives you, if you calculate this, this will give you an effective action with power suppression in m square. You'll see. Okay, so the effective action is this thing, and I put a CS. And remember, I said that if it's a vector, if it's a complex scalar, the coefficient was -1, and if it's a real scalar, the log of that delta operator will give you a -1. So this depends upon whether this is a complex scalar, real scalar, and also if it's a fermion, it's the same way. You square the Dirac operator, get a scalar operator, and then for fermions it is 2. Okay. So this tells you the degrees of freedom for the thing that you are dealing with.
So, how do you relate these coefficients with the Wilson coefficients?
So these coefficients, so basically what happens is, this coefficient will give you the like u square, u cube, etc. And this whole thing, this whole coefficient are the Wilson coefficient.
So you equate it.
Yeah, because this is my effective action. And I said that this will give you a power series in 1 by m square times some u square, u4, etc. Which will be a power, this thing in fields. And whatever is the coefficient, those are the Wilson coefficients.
So far, all this is at zero temperature.
All zero temperature, yes. Okay, so this is all. So this is done in various things. For instance, in GR, there is a Euler-Heisenberg Lagrangian where you integrate out the electron and get just the gauge field background. So that is can be also done this way. In gravity, you integrate out massive particles to get the theory of this thing. So in this particular case, our interest is to keep track of this mass square as the particle whose mass, heavy particle we are integrating out and keeping track of the 1 by m square. So this is the slant for doing it in this way, but this is a general thing. Not you can do it for different theories. Okay.
So you are in the free, like you don't have the potential, right?
No. So what I said was that this was the three theory. Then I said that you multiply that with the power law, and this full thing is with the potential. Okay, this delta has a potential, delta zero didn't have a potential. So now I have to solve for this full series term by term. Now, okay.
Did delta zero have the gauge field?
Yeah, because delta zero does not have the gauge field. That's a tricky question. No, I don't think that had a gauge field. It's a free theory, but well, as a simple this thing, it does not need to have a gauge field because all it contributes is a Tm square. So basically, what you do is you take a free theory without gauge field, without the U, okay, and you write the full theory on top of that. So the free theory is your choice. I think it's simplest not to take gauge field because then you have the thing here, the solution here. If it had a gauge field, I think you will have some activities etc. here, which will complicate things. So the delta zero does not have gauge fields, and the delta has gauge fields. Yeah, so that thank you. That should be pointed out. So delta zero was this one, no gauge. Okay, so I do this. I put in my solution. Remember when I had a k at the coincidence limit, the free part was just this coefficient times Tm square. The x minus y part doesn't appear, and this is my hk, the series. So then I can do this integral first in t. To do that, I change variable Tm square is tau square. Okay. Do this integral in tau and use the fact that this is the integral representation of gamma function. Okay. So this whole thing, after I do this t and tau integral, which is a tau integral, I get this series in k. So I should have pointed out that it starts with k equal to 0 to infinity. So in integers. So this is my actual Wilson. This is my effective theory, and these guys are my Wilson coefficients. Okay, to all these V0, V1, etc. So for regularization, we use the same techniques. So this will be infinite because at k equal to, when you actually calculate it, this gamma function will become singular at d equal to 4. Okay. So what you do is you calculate it at d 4 minus epsilon, okay, and carefully take the epsilon 0 limit. Okay. So for this thing, you introduce to keep the L dimension 4, you put a mass dimension to the power epsilon because you're going to, and the previous calculation gave me this power series. Now see, this power series starts with high power of m, so m4, m square, m0, and then 1 by m square, etc.
So this thing will be different for even dimensions and odd dimensions because this.
Should not be. It's the same. Because what I do in finite temperature is that T0 will be time temperature will be different, and I do the three-dimensional case, it is the same story. The answers will be different. I mean, the expressions will be different, but the procedure is not going to be different. I will do this calculation in 3 minus epsilon dimension if I am talking about 3 dimensions.
Because k is integer.
Yes.
And this d by 2, if d is an odd dimension,
Mm-hmm.
then k will never be d by 2. Yes, d by 2. In that sense.
Yeah, how does that matter? So if you ask,
So, yeah, so this will change the result.
okay. So I see what you're saying. So what actually is done is, I mean, I haven't done the actual three-dimensional case. What we do is we start with 4 dimension. So D is 4, and then we make one compact. So D still remains 4. So what happens if you actually take a space-time of 3 dimension? I don't know. I have not done that. Yeah, thank you. That is a good point. That even in the thermal case, there is 4 dimension, and you do heat kernel in 3 dimension. And I'll come to that. Okay. So you use this identities where you isolate the pole of this gamma function and use the fact that this is epsilon log. So what you find is that when you write it out, this 1 by epsilon cancels this epsilon here to get finite log terms. So you'll see some finite log terms. Also, there will be 1 by epsilon still left, which you should have enough constants in a renormalizable theory to absorb with counter terms. And for higher dimensional operator, you should get finite terms. Okay? You should not get any of this epsilon thing at all.
These gammas also might be in previous steps. Those might be coming from finite computation. I mean, not. I mean, were there some divergence in the integral? I mean, how these gamma are coming in the steps in the previous steps? I mean,
This gamma is coming from this integral of d tau. So it's not coming from any loop integral. Okay, so this is a different way of calculating. We are not calculating diagrams or loops. I'm saying it's the same physics which you will get when you do the loop.
But still it's one loop effect.
It's a one loop effect. Right? So you get the same algebra at that point.
I mean, when this key starts from 0, right?
Yeah, let me show you. So you have an m to the 4 term, m square term, and so on. Right? M to the 4, m square, m to the 0, and
I mean, never this integral diverging. This integral, I mean, when k is.
yeah. So because this is divergent, you have a divergent term which is absorbed in this thing at d equal to 2. Okay, that we have to isolate, and we have to find ways in which we should absorb those divergences. So as I said, the divergences one kind will cancel. This epsilon will cancel this divergence, and you will get a finite log term. Other ones you still have a 1 by epsilon, but you should have in the theory counter terms in the renormalizable theory to absorb.
I think 3 dimensional also you will be having such divergence.
Possible, yeah.
And then even finding it there.
3 dimension, I mean 3 space dimension, as I said, I haven't done, so I don't know. I don't know the comment. What you get there?
So 3 means 2 plus 1.
2 plus 1, yeah. In this, you'll see there are 3 special dimensions and 1 time dimension which becomes this thing. Okay. So this effective action without gauge fields looks like this. Okay. So we still have to know what is B0, B1, B2, etc. Okay. And I'll give you the answer. This B0 is identity. B1 is, I'll show you how that comes, but just to have what you will get finally. And this is the series you will get. If you turn off the gauge field, then just keep a potential. Okay. So now you can see that this is just in terms of effective action, this is just a thing without any field. So this is a cosmological constant. If you don't know what to do, you drop it. But when you want to do a Coleman-Weinberg type of calculation, then you say that this mass is that your Higgs mass is field dependent Higgs mass. Then you put that field dependent Higgs mass here, and this first term will give you the Coleman-Weinberg. So, but Coleman-Weinberg, remember, is only for a constant field. It's not a effective theory. It's called effective action, but it's not like you can take those terms and draw Feynman diagrams and calculate scattering vortices from there. So this is the quadratic term which you draw. This is the mass square. So U will be, as I said, it's phi square. Phi square will get normalized by a mass square, which is known. This is quadratic mass. So this whole thing you have to absorb in the renormalization of the mass. Okay. There is another term here, which is V2 will be U square. So this will be renormalizing your lambda, the couplings, and you will get terms of. So this is the answer. This is the cosmological constant which you drop in effective action, but this will make sense if you do Coleman-Weinberg. This is renormalization of mass. This is renormalization of the lambda which is there in this. So U square will give you this lambda square 5 to the 4, and the higher order terms will be powers of U suppressed by powers of M.
Is
And
model a free parameter?
no, sorry, I copied this from a different place. So M and this M are the same. Thank you. So this is the mass which we are integrating out. Okay, so this is my effective theory at zero temperature. Okay, and you get similar thing. So
Coleman-Weinberg, you won't get the last term. So the difference.
Coleman-Weinberg, you only deal with the first term because what you say is
You
M.
also get M square and M power 4.
What is it? M square.
And M power 4. Mass square corrections.
In Coleman-Weinberg.
Yeah.
You are talking about finite temperature or the zero temperature?
Zero difference. Finite corrections are there for masses.
You can write, I mean the whole thing, you can write it for a constant field, keep all the terms.
Right.
If you want.
Yes.
Yeah, that's it.
But you don't get the, like you said, the last one because
Which one? M to the zero.
series.
So this series is like a 1 by m square separation. Okay. So I will show where if you put in background gauge fields, then the V0 is just identity, V1 is this, V2 is this, and so on. So these gauge fields come in if there is a d mu as a gauge field. So now you see that depending upon what you have in mind, supposing you are just doing cosmology, you don't want any gauge fields in the background, you can switch off these gauge fields and just have U square, U cube as your Heat Kernel coefficients. On the other hand, if you are doing this Casimir effect, for instance, where you want to find out what is the effect of the gauge fields after integrating out a mass, then you calculate these terms. So depending upon the applications, you can go in different directions from the general type of formulas. So heat kernel coefficient, now how do you actually calculate them? You put back that in the heat equation, okay, and this K, and after taking out the constant part, what you get is that H depends upon this equation. Okay. So you write this series for H, put it in this equation. What you will get is a recurrence relation between this Bk and Bk minus 1, which will depend upon this potential and D square, which contains the background gauge fields, and this Z. So here it's important to keep Z. At this point, you don't take the coincidence limit. What you do is that you calculate, so you know that you start with B0 is identity, calculate B1, and then put it B1 here and calculate B2, and so you do it in iterative. So you can do an iterative calculation. Start delta and no, delta is the full operator, which is D square plus M square plus U. So D was my original. This D, I divided it somewhere. This one. Okay, so with this, U in the second, the thing. These are the Heat Kernel coefficients calculated iteratively. Okay. And my action was this times the first Heat kernels, this times the second, and so on. So I have the full effective action calculated this way. So what is relevant here is basically the commutators of this d mu give you the g mu. And you solve that, this equation, the iterative equation. Okay, anyway, this equation. Okay, so with this, I'll go to finite temperature. Okay. So here there is a lot of horrendous algebra. So I'll skip the boring algebra, but I'll slow down at the important algebra where there is a regularizations involved. So what do you do if you do that at finite temperature? We want to calculate this K. Okay. So this K, we said that this was my trace of X. Convert that to a trace of P, okay, by putting in a complete set of P states, okay, and here, and use the orthogonality of these P states. So what you will get is this. So here what we have done, we have taken a d plus 1 is 4, where d is 3 and that extra is time. And what we do in finite temperature is basically we take this P0, the frequency, okay, to be discrete. So this is 2 pi I and n being an integer for by beta. Beta is 1 over t. So basically 2 pi n t. This is for bosons and this is for fermions. So when we substitute that here, I mean we take a discrete sum instead of an integral. That gives us whatever action here at finite temperature. So this is what's called the imaginary time method. So here you don't have to do Feynman diagrams and put this propagators as imaginary time propagators with finite temperature. Here you just sum over the in the d4 p, you just sum over the frequency.
So that
How does it use to epsilon?
Well, that's why just for convenience, you can, I mean, this you can take epsilon and it will the same story.
so at n equals to 0,
Yeah.
P0 is non-zero for fermions, and for bosons P0 equals to 0.
Right. So it has this thing that for fermions there is no zero mode. When I sum over n minus infinity, there is no zero mode for, sorry, for bosons there is no zero. So in this there are two e to the pi, one coming from this side I and one coming from there, and inside there are in this derivative there are the differential operators. So this acts, this is the shift operator in the momentum space. Okay, this. So I use this shift operator inside the. Okay. So there is shift in the ith component, which is here, and the shift in the zeroth component I take separately, because in this I will find that this A0 is actually observable. This is what's called the Polyakov loop. So at finite temperature, this A0 plays a role, which is a non-trivial part of this calculation, that you will see contribution from this A0 if the particle that you are integrating out has some gauge interactions. Then there is the extra Polyakov loop contribution which will play a role in this. So now you see that basically this has become a shifted dp, the ith part, and there is a q part which is the zeroth part of that shift operator attached to a u. Okay. So this is like a Heat kernel for the 3 dimensions. Okay, d is 3 now. Okay. So what I do is I take this Heat kernel coefficients for the 3-dimension theory, which I calculated in the same way which I explained. Okay. And then I calculate with this q square coefficient. So Heat kernel with u shifted by q square and di square. But there is one catch here, that this q is not a q number, c number, it is operator. So what you have to do is basically put this and use, so I'll, yeah, use commutators so that you, when you operate with q, okay, the q comes to the right and it doesn't operate on the, So the derivative part gives you a field, the diq gives you a field, and the space part, the a0 part remains as your q number. So you have to use enough commutations inside that to calculate that. So basically this is the Campbell-Baker formula to calculate these commutators. So with all this,
What about the gate choice?
so gate choice is, in this, the gate choice made is that A0 is a constant. So normally what happens, you take A0 equals 0 and you do your calculation. But then Polyakov show that it's, if you take A0 as a constant, then the A0 is actually playing a role as a dynamical variable. I mean, it's a thing which has an observable consequence. So here the gate choice is A0 is a constant. So let me show you. Okay, I'll skip all this.
So here we have 3 degrees of freedom.
3 degrees of freedom.
So because A0 is not equal to 0.
Yeah, so there is a A0 there is a mass, and there is a U. U contains the potential. So I have this, if I can calculate these guys, then I have this heat kernel coefficient times this whole thing as a function of beta. Okay. So this is what I'll call my, so if I stick in all this, that thing here, this is the integral I have to do with this extra q's. So let me explain what are q's. So here is what I was talking about. So this was introduced by Polyakov. He said that at finite temperature, okay, at 0 temperature you can take A0 equal to 0 and it's perfectly a good gauge choice. But here, if you take A0 as a constant and take this observable, which is called Polyakov loop, then this actually is something which has a physical consequence. So the way he introduced was that he said that if you have quarks, the quarks are bound and there is no A0 associated with it, but you have high temperature. Okay, so you have a free quark, then you have this gauge field associated with each quark, a Polyakov loop associated with each quark, and that should have a measurable consequence. So what people did was calculated this Polyakov loop potential, that if you have two guys in Polyakov loop, what is the potential and so on. But in this theory, what I'll do is I'll just calculate the thermodynamics of this guy. So having free quarks and having free quarks with Polyakov loop will give you different pressure and so on. So I'll just concentrate on this guy, that what it does to the thermodynamics in this, because basically we are interested in the finite temperature property of this. Okay. So I said this Q, after using the commutator, is just A0 plus IP0. This IP0 is the guy which is summed over, okay, and A0 is this log of omega, okay, 1 by beta, because this is 0 to beta. If it is a constant, it's just beta times A0. Its log of that guy is just A0. So here I have this, which is Q. So I have N, which is an integer, okay, which is coming from my Matsubara frequency, the frequency which a discrete frequency is summed over. And this is the log omega. So I'll call this N tilde. Okay, this is the real list. So this is a contribution which is coming from my Polyakov loop. Alright, so I have things like this now as my Heat kernel coefficient. Okay. So if I define a quantity R, N and R like this, okay, I have this whole thing written as a gamma function. So you can do the t integral, it will be t to the r and t to the nt, and you can do this and you will get a gamma function times this. Okay. And then there will be a sum over n, because this is the thing that you need to sum over. So finally, this is my thermal coefficient for heat kernel. So it's our Render's expression, which involves various things. Okay. Now, this n tilde is my Polyakov loop. It's just the log of that omega, A0 basically, and n is the integer that you are summing over. Okay. So this has mass and it has this Polyakov loop, and the heat kernel coefficients have this u's. Okay. So these are just the Wilson coefficients of the heat kernel. Alright, so I will skip this. I just do quickly. You are calculating something like this. So what you do is, if you take G of this kind, take a d by d kx. Okay, so where you introduce x, so I have defined my g like that. K derivative of that will bring out this n by n to the power k, and I put in a prefactor such that the rest of the things will cancel when I do the k derivatives. So this is equal to taking k derivatives of this guy, and now we need to calculate what is this guy. Put it back and calculate k derivatives. I won't bore you with this. So this type of maths also is done by people who do this Casimir effect. So this Elizalde has a lot of papers in this Casimir effect and 0 point energy. So we use a sort of identity which they have actually proved, but we can take it and so that gx which I defined gives you something which is a sum over the cosine of something and a Bessel function. So I'll write it a little more clearly. So here is that thing written in a neater form. So this different I zeros are coefficients of these different Heat kernels. So this is for the first, the m to the 4 term. Then this is the mass square term, and so on. And this is 1 by m square, and this is 1 by this is 1 by m square. This is the mass zero term. Okay. So this is the zero correction. So this is the basic quantum correction at zero temperature, and then there is a finite temperature correction. Okay. And so it neatly looks like the finite temperature corrections are something which are like Bessel functions. Okay. N tilde is your Polyakov loop, that is basically A0, which comes as in the cosine. And you have the series 1 by n square k2, 1 by n k1, and so on. And you will get these various things. Okay. Now to make contact with what we know, okay. This thing, the first two, so what I will tell you is the first two things are known in a different language and the remaining are new. Okay. So what do we know in the first two? So this is my, let's drop the Polyakov loop, so the cosine is dropped. So this is my, what I call my zeroth order quantum correction, which is useful for the Coleman-Weinberg, and this is the thermal part. Okay. So this, remember, has no fields. So basically this will give you the the effective action, which is negative of the V. So this is minus V, and that is actually P. So this actually gives you the pressure. First one is the pressure. The second term is a product of U times something. So that is giving you the correction to the mass. The next term will be the correction to the lambda and so on. So you have a correction to different orders in the effective action. Now this guy is seen in a different way. So we know what is the correction to the pressure from a different way of calculating, which is this. So if I take this m beta, so beta is 1 by t. So if I take m beta to be small and I try to do a series expansion of this, okay, it does not work. I will not get this. This is a well-known thing. See, this is the pressure for the bosons, this and so on. These are corrections to the pressure at high temperature. Okay, so this is the well-known expression. So what I want is that I want to go from here to there, okay, and so a naive series expression doesn't work. Okay, you can think that okay, there are asymptotic expansion for this Bessel function for small argument, and then I can do a 1 by m square expansion of that. But and if I keep a few terms, I'll get these few terms, but that doesn't work because you'll see that for each coefficient of this, there is a 1 by n square series as a coefficient for each m beta power. So each term is divergent. So basically the bottom line is you have to regularize this. It doesn't work just by putting it in Mathematica and taking a series expansion. So this is the main thing. So basically I'll show you that method of regularization. If you work out for one, then you can work out for the remaining. It's the same story, and you can also put in the this guy, the Polyakov loop, calculate everything. Okay, so the way that works is we use this, or this is used, that is called Ramanujan master theorem, that any series of this x being a complex number, if you can express it as a series with this 1 by k factorial and a coefficient, okay, then this has a Mellin transform for the form that same phi s and gamma to the gamma s. So this was proved by Ramanujan. So basically that helps us in taking Mellin transforms of various expressions. Okay, if I can express that as a series. So this was used for a sense that you can express this as a series in x, okay, and then by alpha, that is another series. Take its Mellin transform and use the Ramanujan formula, you will get this gamma. So one gamma came from the Ramanujan formula, the other gamma came from the series expansion of this K. So that's why you have two gamma here. Remember, I have to some Bessel series over. So what I am looking for is 1 by n square k or 1 by n k Bessel series of this kind. So if I take the inverse transform, so if this is the Bessel Mellin transform, the inverse transform is that you take this guy x to the minus s ds over a strip where this sigma is the real value of s. So over a thing where this is regular. Okay. So so this is a vertical strip where this function is regular, and you close the loop where and pick out the poles of these gamma functions. So that is the whole thing. So this is the inverse Mellin transform, which has two gamma functions. So the nice thing about gamma functions is they will give you those isolated poles. Then I have a sum over n alpha of this, where this x now I replace by nz, and so I'll have in this x I'll have a n to the alpha. Okay. So when I have a sum over here, basically I'll have a sum over ns here, okay, because it's x to the s. So and this is my zeta of s. So I have a expression, the closed form expression for this sum over this in terms of this gamma function and the zeta function. And all I have to do is do this integral by picking out the poles of this guy. So this is where the regularization is involved. So it is not simply calculating that thing by putting numbers. It's simply something like you do 1 plus 2 plus 3 and the answer is minus 1 over 12 because you've done a regularization. So there is a regularization involved in picking out the poles. And after I do all that, I get that the thing I know, which is this pressure expression. So the first term is the pressure expression, and we have the expressions for all the rest of the guys. Okay. So this is the coefficient of my mass square. So mass square correction, what is the thermal correction to the mass? This is important because when you do the Coleman-Weinberg, you have to put in the mass correction in the formula to get it correctly, including the contribution of the particle which you integrated out, which was the main problem which we started with. This is the thermal correction to the quartic and then higher, this is the higher order operators. So now we have closed form expression for these things after doing all that. So that is it. So for instance, the pressure is given by this. Okay, this e to the 4 by 90 you recognize, and then the rest of the things also are known. And as Sudhir was asking, the leading order in this Weinberg is you put the field dependent mass. So for instance, SM Higgs, the effective mass which is field dependent is this. So you stick in that in the mass over here, and that gives you a potential, the Coleman-Weinberg potential, but you have all the thermal corrections now. So you put in the same mass all of these places, and that is your Coleman-Weinberg for this guy. And if you want to do effective theory, okay, you have to do the same thing for effective theory, that you have to put the second derivative of that power 6 operator, dimension 6 operator, and stick it in here in all the terms and keep order 6 terms. Yes, so basically that's the. So one thing I wanted to point out was that this Polyakov loop contribution is something new people have not dealt with. So this n tilde. So this will be important if the particle that you are integrating out has a gain interaction. So this was originally introduced for quarks, but this is for anything. So for instance, Higgs has a SU2 interaction. So that there will be an associated Polyakov loop contributed to that field. SU2 comes to U1, and also if you have hidden gates, there is a hidden secret garage, this interaction of the Higgs, that will also contribute to this Polyakov loop. Okay. So if you do this one loop thing, including those extra Polyakov loop, you will get something different from what you get from normal phase transition calculations. Okay. So this was, I think, there was enough for this thing. Thank you.
Thanks. Interesting talk. Are there other questions?
In that you cannot expand the small in that part. Like you have this, you cannot match these two expressions. I mean, you have this 1/90 and this small mass expansion.
Okay. So this is valid for high temperature. Okay, m by mt. This is the expansion in mt. When you have a low temperature, then it's actually very simple. What happens is that at low temperature, this e to the power minus m by t. This. So there only the first term. You don't have to do the series because each term is exponentially suppressed. So the leading term is there. So that's you get the Boltzmann formula, and you will get the Boltzmann formula suppression for all order operators.
So I wanted to ask if I expand this part, if I expand in large M, like formally, and then do is that same as you were saying? I mean,
No. So large M expansion, that means M beta is the correct expression. Large M beta, that means low temperature lower than mass. This will give you that e to the power minus m by t.
yeah, but maybe I mean, if I keep
And that doesn't need regularization. Just leading terms, if you calculate, you will get the correct answer. In this, you just put in the asymptotic formula value for the formula for this k. For
no, I am just saying I define different calculation. If you can keep all the terms for this basis, you know the infinite expression in terms of this exponentials. And if you do the integral, I mean, if you can do this somehow representing defined way, can you get the same answer? I mean, maybe it's the same. I mean,
you are saying that no. That actually some of this involves a series expansion. It is m beta. So that method which I talked about only works for m beta small. So I didn't explain that, but this expands a series expansion which involves a m beta small. Whereas if m beta is large, that means mass is greater compared to temperature, then I do a different expansion of that k, and that gives me my Boltzmann suppression. So that part is very and corrections will. But that part doesn't need regularization. So that's a simple thing. So the point is that this is all unified here in this heat kernel coefficient. So if you have so depending upon the temperature, if your temperature exceeds your mass, then you have this, if you use the correct formula, then your heavy particles which you integrated out will contribute to the heat part. That is the thing. So that's built it into the this one. Okay. And we haven't gone back to check the actual phase transition, whether it is solving the problem or not, then my collaborator thinks slowly of actual applications. He only wants to do this maths. So,
so you can only do a small mass. The destination is small mass, right? That is the
no, it's not mass, see, it's m by mt.
M by T, so that
It's not m by t, it's m by t, yeah.
M by T, so that ratio has to be small.
Yeah, so high temperature, basically given the mass, the temperature should exceed the mass. This is the thing which you are looking for, right? That your temperature should exceed your mass so that you will have a change in the potential. So we are looking for the high temperature application.
I have a very basic question.
Yeah. Okay. Yeah.
So I haven't studied items or everything. Are there any experimental evidences of the predictions made by items?
Well, that's a very broad question. Yeah, finite temperature theory is everyone's theory. So I don't know the detail, but look, okay, let's start with this. This is the pressure. Okay, where are the thermal corrections to pressure at finite mass for relativistic? Is there experimental evidence? QGP. but I don't know the details of how much these formulas have been checked.
Like
Thermal mass is a prediction. This m square t square is a prediction. As it been tested for quarks that you have this. Yeah. In electromagnetic plasma, the temperature correction to the mass is known. Yeah, so electromagnetism does this thing. Okay, and this, as I said, this thing with the m cube term is what is important in the phase transition that comes only in the scalar. Because if you write it in the field dependent, m is, let's say, y times phi. Okay, then it is phi cube t. So potential has a minus phi cube t, which gives you that coming down. So it is phi square minus phi cube t and then phi to the 4. So you need this guy for phase transition a large.
So at beginning of the talk, you said that so this will induce gravitational waves. So we can.
No, any phase transition will induce gravitational waves. The first order phase
So we
transition.
can constrain we can constrain some range of the parameters of this theory using the predictions of the.
Yes. So that is the idea of all this phase transition, that you predict, given a theory, you predict the gravitational waves and see if it's there in PT or not, and that will constrain your.
So has such constraints been given?
Well, people have predicted various phase transitions at various temperatures, and nothing has been measured yet. So that is the thing. Your measurements are, you have some good plots in your paper where you take different phase transitions at different temperatures, and so the point is that the sensitivity of the gravitational wave experiments are not enough right now. But PT etc. are coming down, and this advanced LIGO is also coming down. So right now there is. Yeah, you have a question.
Well, I wanted to ask about the gauge dependence. So for an
Yes.
potential in a theory where the scalar you're capturing potential for is Higgsing something, like the standard model of SU2 that you mentioned, then the effective potential would be gauge dependent. Do you capture the gauge dependence here, or
No.
are you not thinking about it?
We are actually on that now. So what happens is, in standard model, it's the gauge boson integrated out. It give you that minus I cube t. Okay. But in that integration, it depends upon the gauge you choose for doing that calculation. So that effective this thing is gauge dependent. So Ramsey Nussolf has a paper which discusses this nicely. So in this we did not integrate out gauge bosons yet. We put the scalar and fermion integrations out, and we just put the finite temperature.
So we talked about gauge theories, you mentioned both QCD and standard model of SU2 for the Polyakov stuff. But I guess the gauge interactions you're capturing there are more QCD-like.
Yes. Yeah, that's a different thing that people have not done before, this Polyakov loop, except in QCD, but that should be there for any gauge interaction. But we have not yet addressed that issue. So that's an important open question, that if you integrate out gauge boson, then this becomes a side-dependent quantity, and that is still not the thing. So that is open problem, and how to do that correctly. So that is something that.
Which the result coefficient changes is the point, right?
It changes in the sense that if your temperature becomes equal to the mass of the guy you integrated out, then it's an important thing. Because then that thing is there in the heat bar. So that was the first problem I addressed, that if your temperature exceeds the mass that you integrated out, then this is the important Wilson coefficient. Otherwise, if the m is much larger than the temperature, then these Wilson coefficients are Boltzmann subset, e to the power minus m. So then they won't matter.
Even when they start with mass equal to 0
Mm-hmm.
and allow other, I mean, whatever you are doing.
Yeah.
So then finally maybe the mass, some mass like that.
So no. So what happens here is that we are doing it in a. So how you treat this with the Heat kernel expansion? The way I did it, that Heat kernel expansion became a 1 by m square expansion. So you needed a heavy mass to integrate it out. So what do you do when you want to integrate out a zero mass particle? I don't know. It makes sense to write effective theory integrating out a zero mass particle. I have not seen an example where this is done. For gravity, for instance, you integrate out heavy particles, other massive particles to get effective theory in the gravitation. So I mean quadratic and quartic. So you in this, it's always a heavy particle which is integrated out for convergence of this.
So in QED, for instance, the Euler Lagrangian, electron is integrated out because it's heavier than the. Yeah. Okay. Thank you very much for starting on this such a busy day.